Bismillahirrahmanirrahim. So this is 0620 IGCSE Chemistry Paper 6, which is the alternative to practical. And question 2, we had attempted some of it. So this is a titration experiment, right, with two solutions of sodium hydroxide labeled A and B. We've got the equation for the neutralization reaction over here. All the details, right, the readings were taken, put in over here. Right, color change of thymophthalene, I believe it was. Yes. Right, which one is more concentrated? The solution A is more concentrated because it requires more HCl. The ratio of concentration is 2:1. Right, and state the volume of hydrochloric acid needed in experiment 1 if experiment 1 is repeated using 10 centimeter solution A. Right, and so we did that. Got 10.16. Now this is the point till which we had reached. Moving further, let me get my pen. Okay, so in experiment 2, which is the one with solution B, so the same titration solution B of sodium hydroxide, the conical flask is rinsed with distilled water. Oh, by the way, right, for your ATP, right, good thing is that over here you have all your tests.
Oh, okay.
Test for anions, test for aqueous cations, test for gases, and flame tests.
So they will be in every ATP. So like we don't need to memorize it into head,
For the
right?
ATP, right? And obviously you have, oh, this one doesn't have the purity because they're not going to ask you questions about MR and stuff,
Yeah.
right?
Okay.
This is obviously focused on the practical application, practical aspects.
Yeah.
So
Okay.
good thing the tests are given over there. So suggest why the conical flask is rinsed with distilled water.
To remove any impurities,
Okay, just a sec.
like to remove any impurities left over from previous experiment or from the air.
Right. So to remove, yeah. So you said stuff left over from experiment 1.
Yeah.
Right. That would be correct. Right. Saying impurities won't apply over here because you're not using a new conical flask. Okay. You're using the
Yeah.
same one, and so there would be maybe slight excess, sorry, of hydrochloric acid, or maybe traces of sodium hydroxide on the upper walls, and that could affect your results. Right. So to remove the, what should we call it, right, substance, chemical left over from experiment 1. Okay, the conical flask is not dried after it is rinsed. Why is it not dried?
Mm. Karan, you can answer that.
I don't know.
Wait.
Right, so whatever distilled water is left clinging over there is not going to affect the molarity of sodium hydroxide.
So it will not change the number of moles.
Yes. Right, in this case the molarity would be affected because you had a solution of higher concentration, right, and now you're adding a solution of lower concentration, and so obviously if there's any leftover droplets or something or from the higher concentration, it's going to affect the molarity overall. Distilled water is not like a smidge of distilled water is not going to have any effect. So it does not change or affect number of moles of NaOH solution. By the way, you can write beneath the line. You can use this blank space if you want to. You probably, like, I don't know what you'd be writing for 1 mark, but you can write here, you can write here, so you can use any blank space there is in the paper, right?
Yeah. Okay.
As long as you label what you're writing correctly. Again, if you need to, that is. So state the effect, if any, on the volume of dilute hydrochloric acid used in experiment 1 if the solution of sodium hydroxide is warmed before adding dilute hydrochloric acid.
Acha. There will be no effect on volume.
On the volume of hydrochloric acid needed. Okay, so no effect. Now the reason is what?
That's the reason is wait. Because the ratio is 1:1 between the hydrochloric acid and the sodium hydroxide.
That is the ratio in the equation, right? So what is actually happening?
Okay. So okay, if we change the temperature, it affects the rate of the reaction as well.
Rate of reaction, meaning that as soon as a drop of hydrochloric acid uh, comes into the conical flask, right, it will react faster with the sodium hydroxide.
But it won't change the amount of.
Exactly, right? Temperature does not affect concentration of NaOH. Okay, suggest how reliability of the
Uh,
results can be confirmed.
Repeating the experiments.
Yes, so remember, reliability, repeatability. Right, R and R.
Yeah.
So repeat the experiments. Another thing, and compare results. Okay, so you need to mention repeat and compare. Suggest a more accurate method of measuring the volume of the solution of sodium hydroxide. So what were you using right now? You were using a measuring cylinder. How can you be even more accurate?
Burette.
No, burette is for the acid.
Uh, Pipette. I don't
Yes,
know if I'm pronouncing it right.
pipette. Right, in this case, I mean, you could use a burette. They have given that as in the mark scheme. What is important to mention is volumetric. What does volumetric mean?
It has volume.
It has a defined volume. Right, so you have pipettes that are 25 cm cube. Right, and so in that pipette, so they've got this bulb, and then, right, and so they've got this mark over here. If you fill the liquid up to the mark, it is exactly 25. Right, so more accurate compared to using a measuring cylinder. Right, now I say pipette because that's what you normally use to measure out the alkali. Right, you don't normally put an alkali in the burette, but again, normally does not mean you can't. Right, so It's what you said initially, that works, but the key word over here is volumetric.
Okay.
Okay, aqueous sodium hydroxide reacts with aqueous barium chloride to form a white precipitate of barium hydroxide. Use this information to suggest a different method of finding out which of the solutions of sodium hydroxide, A or B, is more concentrated. In your answer, state how your results would uh, how your results show which solution is more concentrated.
Hmm. So, like a more concentrated solution has more moles of reactant per unit volume.
Hmm?
A concentrated solution has more number of moles of reactant per unit volume.
Yes.
Okay. So we have to tell the procedure.
Yes, so it's 3 marks, so 3 points. Now, in such kind of cases, right? What you and there's a planning question coming on later, so you need three things in general, right? Because 3 marks. You need what is called the independent variable, right? For the planning question, which is I believe 6 marks, you need other points as well, but you need to mention what the independent variable is in this case, in this particular question, I mean, right? You need to mention what the dependent variable is, and you need to measure, right, how to get or process.
In this question, we have to compare the concentration of both solutions.
Okay, so you don't know what the concentration is, right? Over here, right now, you're just trying to get which one is more concentrated. So, right, first of all, what is the independent variable? Do you know what independent variable means?
That doesn't depend on other.
Yeah, so this is the one that is in your control,
Okay.
right? Which
Yeah.
is solution A and solution B. So you've got two different concentration in this case. Although it is unknown, but still, right? That's kind of independent. The dependent variable is right something that
Depends on the other.
depends on the independent.
Yeah.
Right now, of course, it doesn't fit in directly, sort of, but right, the barium uh, chloride solution, that is the dependent variable over here. That's what you're reacting with. And how to get results? So, right, getting the barium hydroxide. So, what you're going to do over here, very plain and simple, right?
Take a fixed or equal volume.
Yes, measure equal volumes
Like how
of
smart.
yeah, so you get how to do this, which is good. Solutions A and B, right? Use equal volumes of barium chloride, plus barium
To both solutions.
chloride,
Yeah.
right? And then what you can do is you can take the mass of barium hydroxide formed, right? So measure mass of barium hydroxide formed. So which one would have more barium hydroxide?
Uh, the one who has more
The more
moles of
concentrated,
reactant.
yeah, the more concentrated one. So, right, the more concentrated, oops, let's just see, sodium hydroxide solution will result in more barium hydroxide being formed. And you get your 3 marks. All right.
Yes.
Does this make sense?
Yes.
Yeah.
All right, let's carry forward. So a student tests 2 solids, C and D. Test on solid C. Test on solid C. Solid C is iron 2 sulfate. Okay. So he's taking iron 2 sulfate and he's conducting some tests on these things. Complete the expected observations. The student dissolves solid C in water to form solution C. The student divides solution C into 3 portions. To the first portion of solution C, the student adds, so you got iron 2 sulfate over, right? The student adds 1 centimeter cube of dilute nitric acid, followed by a few drops of silver nitrate. What's going to happen?
Oxygen will be released.
Huh?
Oxygen will be released.
Why?
Okay.
Iron sulfate is a salt.
Oh yeah.
There will be no change.
So sulfate, right? These are the anions, and for sulfate, the test is nitric acid and then aqueous barium nitrate, not silver nitrate. Right, silver nitrate is for the iodide, the bromine, and the chlorine. Right? And so what this guy did was is not a test. So you're not going to get anything out of it. Right? And as far as iron is concerned, you add sodium hydroxide and aqueous ammonia. So adding nitric acid is not going to give you any result for the iron either.
Hmm.
Right? So what you're getting over here is nothing. So no observation is no change. Nothing happens.
Yeah.
Right? No change or no reaction.
Yeah.
Okay, to the second portion, he adds dilute nitric acid followed by a few drops of aqueous barium nitrate. Now, this is where we get it, right? You have nitric acid and then barium nitrate. So, what are you expected to get because you've got iron 2 sulfate?
White precipitate.
White precipitate. So, you should get a white precipitate out of this. Right, and then finally, you have right. The student adds aqueous ammonia dropwise and then in excess. So this is testing for the cation, right?
So
And
clockwise, a green precipitate is formed.
yes, and right. So there's a green precipitate, and insoluble in excess turns brown near the surface on standby. You can just take all of that and write it down.
So wait. Okay. So the answer will be only green precipitate
No,
forms.
no,
Then it would be in excess as well, right?
yes, because first they're saying dropwise, then they're saying excess. So that's 2 things, and you also have 2 marks for this guy. So you need 2
Okay.
points,
So
right?
dropwise, a green precipitate is formed.
So you can use PPT, green precipitate forms.
And in excess, the green PPT remains insoluble.
Insoluble in excess. And you get your marks.
Okay.
Now, solid D. they are not telling us what solid D is. So we just need to go
Wow.
with tests. So table 3.1 shows the tests and the student's observations for solid D. For tests 2 and 3, the student dissolves solid D in water to form a solution. The student divides solution D into two portions. Right, so does a flame test and you get an orange red color. Then you're adding aqueous sodium hydroxide dropwise in the excess, and so you get a white precipitate with no change. And then you are adding uh, right, nitric acid followed by silver nitrate. So first of all, for the flame test, so let's just take a look at this. Right, you're getting orange red, which means you've got calcium. So the cation you have is calcium. You can also check it over here. So for calcium, right, uh, for sodium hydroxide, you get a white precipitate that is insoluble in excess. So that checks out. Now you'd say that, well, you need to do it with aqueous ammonia to be sure. For any of these tests, you need one, you need to conduct any two tests to support. Right, so the flame test was done first, and right, it clearly says orange red. So couple that orange red with this observation, and then you
Calcium
get
chloride.
and yes, right, and then you get a white precipitate with this, and so you have CaCl2.
Yeah.
Okay, so describe how to do the flame test in test 1.
Clean the wire loop.
Use a clean wire, not clean the wire, use a clean wire
Yeah.
with,
Use a clean wire.
so use a clean wire with solid sample. Then you need 3 points.
Observe the color.
Well, to observe the color, you need to put it into the flame first.
Prepare the sample.
Put it into the flame.
Yeah. Sorry.
And then observe flame colors
Okay.
and record observation. Okay, and we've already identified the solid, right? So that is CaCl. And just writing this much gets you both marks. Okay. And finally, the planning for 6 marks. So the label on a bottle of orange drink states contains no artificial colors. A scientist thinks that the orange color in the drink is a mixture of two artificial colors, sunset yellow and allura red. Plan an experiment to show that the orange color in the drink does not contain these two artificial colors. Your plan should describe the use of common laboratory apparatus and samples and the orange coloring of the drink. You may draw. Acha. First of all, right, you may draw. So this is optional but suggested. Why is it suggested? Because if you're able to make a proper illustration of what you're doing, then even if your explanation is falling short, it will really help the examiner understand what it is that you are trying to say. Okay. Anyone there?
Yeah. Yeah.
Now, question is, what are we going to do? Do you understand what they're asking you? Where this is coming from? Anyone?
Yes, let me analyze the question. So we should like write the materials and apparatus that we use, right?
What kind of experiment will you be conducting? Is it going to be a titration? Is it going to be what?
Experimental procedure.
Yes, what I mean, if you're going to write an experimental procedure, but what? Or what kind? What type?
Mm,
That's the first thing you need to identify.
yeah.
Are you able to sort of get to that?
I mean, kind of.
Yeah. Okay, so what's your guess?
Uh, okay.
Okay, we're talking about colors. What experimental procedure have we learned to deal with colors?
Spotting.
Spotting is done in which experimental procedure?
Uh,
Or experimental technique, let's say.
we need to use a capillary tube.
Capillary tube?
No, wait.
Okay, let me put it this way. Colors in
Uh,
Latin, I believe, are called chroma.
okay.
Does that ring a bell? Aram?
Yeah.
Hmm?
Yes.
Does it ring a bell? Which experimental technique will we be? Because obviously, if you're going to explain for 6 marks the experiment technique to be used, you first need to know which experiment technique is going to be used. Then you're going to get to explaining.
No.
That's logical, isn't it?
Yeah, obviously.
Yeah. So which experimental technique are you going to use?
Titration. Oh,
No.
not titration.
I've pretty much given you the answer. Chroma. Chroma what?
Paper chromatography.
Yes.
Oh my god.
It's chromatography. Right? Now, if you remember, do you remember how chromatography is done?
Uh, wait. We need a beaker for this.
Beaker will come in later. First of all, do you remember the technique? The steps of the technique, how it's done?
We draw a horizontal line
Okay.
about like
So first of all, right, chromatography will be conducted, right, on the juice sample. Right? Why will we be conducting on the juice? Because, right, and right, the artificial colors E110 and E129. You're going to have these three things on the chromatography paper. Next, you said drawing a line, right?
Mm-hmm.
So that is draw a baseline on the chromatography paper. That's one word, no space. Right? Spot samples of the juice, or is it juice or is it drink? Whatever. Right, orange drink. So, sure. And
Yeah.
artificial colors or artificial dyes. On the baseline. Right, and then place the paper into a suitable solvent, and the placement should be below the baseline. Right, then allow solvent to travel up. Up the paper. Right, measure the distance traveled by the colors and the orange drink.
So there are different dyes at different speed.
Well, obviously, right? So
Yes.
measure the distances
And mark the highest point.
and the solvent front, the solvent line
Yeah.
traveled
Yeah.
by the dyes, drink, and solvent. So you can sort of clump all of that together, right?
Hmm.
Calculate RF values and obviously compare. So we actually ended up writing 7 points. Now these 7 points are also 1, 2, 3, 4, 5, 6. These are actually sort of like 8 points in the mark scheme. And right, any 6 would get you marks. So right over here, there's no rule whether you need to definitely include the last part where it's calculating the RF value, or you definitely to include any 6 of like. So basically, right, what they asked, the only thing you needed to mention was the drink and the E110 and the E129. But other than that, basically the planning was outlining how chromatography is done, right? They could very well give you a planning experiment where you're doing a titration. They could give you a planning experiment where you are, right, doing fractional distillation perhaps, or simple distillation, or test for some ions and stuff like that, right? So uh, you need to know chapter 14, right, for paper 6 or paper 4 in case of O level, right? You need to know chapter 14, right? And over here,
With that,
right? Huh?
nothing.
Yeah, I mean, we can leave that, we can put it to rest, right? We are still preparing. Now, obviously, in this particular planning, there was no mention of what we did earlier, right? So the independent, right? The dependent That's not correct. Dependent variables, right? And there was no mention of processing results or processing data. Right, so you could be given a sort of scenario where this is required. So again, depending on what you were asked to do, you might need to include independent. And so when you're doing that, you need to clearly state these are independent values, these are dependent values, this is how you process the data. And then, right, there are right, something called the control, and then they're called, right, other variables which are kept constant. So when you are normally conducting an experiment, again, none of that happened over here, but when you're normally conducting an experiment, right, you only have like one independent variable and you're only measuring that against one dependent variable, right? So for example, if you are you could be given to plan an experiment where you are measuring the effect of surface area of a solid on rate of reaction. Are you with me?
Yes.
Right, and so the independent variable over there would be the chunks or the powdered version of the solid, and the dependent variable in that case would be the rate of reaction itself. And so what are the things you are keeping constant? You are keeping constant perhaps the concentration of the solution that you are using. You are keeping constant the temperature at which you are conducting the experiment. You are keeping constant the mass of the solid that you are using, right? The only thing you're changing is if it's in chunks, right? So those are other variables that you keep constant, and so you need to mention that, right? That this is the independent variable, this is the dependent variable, this is, right, other stuff that I'm going to keep constant. If there is something that you can keep as a control, so a control is a setup where right, you are going to check your results against, right? So perhaps, I mean, it depends on the scenario, so we can talk about that if we come across that sort of plan. And then finally, how will you process the data? So in case of a rate of reaction, you're going to take powdered versus the chunks, and then you're going to, for example, the gas is produced or it becomes hot or whatever the change of, however you're measuring the rate of reaction. And you're going to, so rate of reaction is some observable change, so volume of gas produced, for example, over time, and you're going to plot a graph. So you're going to measure, you're going to mention that there's volume of gas, there's time, and you're making a graph out of that, and so that's how we're going to process all of this. So it depends on planning to plan, right? But in general, all these experimental techniques and stuff that affects experiments is something you need to have a grip on for particularly the planning question in paper 6 or again paper 4 for early. All right.
Yeah, got it.
And we are done. So tomorrow we can start with another paper 1.
Okay.
Oh, by the way, right, again, I mentioned that it's optional but suggested. So just to make a true drawing, right, you sort of have like a beaker, right, and over here, and then you have the chromatography paper, perhaps, right, and you have the baseline over here, and we use a different color, and we have to find what these 3 spots, right, and so you label this. This is the paper, chromatography, right, paper, and this is a beaker, this is solvent, right, and this is the baseline, and these are the sample spots. So some students, what they do is that they explain less and they sort of, right, so they're like, oh, I already given the experimental setup, so I don't need to mention all of this. And so, right, they only, for example, mention these 3 points, right? Allow the solvent to travel up, measure the distances, get the RF value. Why? Because everything else over here is shown as the diagram. Now, the best case is to do both together. That is the best case, right? Again, because if something's lacking in your explanation, it can be made up with the diagram. If there's something lacking in the diagram, it can be made up with the explanation. And that's why it is suggested, optional, but suggested.
It's either you write the explanation and draw the diagram so that it completes both.
Yeah, so again, the best scenario is doing both, right? You can simply give the written text. If it's spot on, you don't need the diagram. You can draw a very good diagram, and so you'll need very minimal explanation with that. So like I said, right, you could skip these 4 points if you do the diagram. I could erase these, and I'd still end up with 6 marks. Why? Because when they've given you the option for a diagram, I'm explaining the experimental setup just by drawing this. It's plain and simple, and I'll get my marks.
Yeah, okay.
Okay, so with that, right, we end today's class. See you tomorrow, inshallah.
Allah Hafiz.
All right, Allah Hafiz.